Hello and welcome back. In this video, we are going to talk about some statistical tools that we would need to understand quantum mechanics. Remember, our ultimate goal is to describe nature, and nature obeys the laws of quantum mechanics. So let's try and tackle this humongous task step by step. Firstly, we need something to label our system. So our first task here is label our system. To do that, what we implement is introduce an abstract mathematical object. And we call it a very strange name. We call this ket. Okay. And what does a ket look like, or how do we represent a ket? We represent a ket with this kind of a signature. Okay. And let's say we used a letter, a Greek letter inside. And let's call that psi. So this is a ket psi, and this describes the state of our system. Okay. And another name for this is also the state vector. And we'll get to the technicalities of this as we progress in the course. But for now, just know that this is a mathematical object. We call it a ket or a state vector. And this describes a system, or this describes the state of our system. Let me give you two examples for this to be absolutely clear what the system is actually meaning. It can be, let's say, the hydrogen atom. There is a proton, and then the electron can be closest to the nucleus, and we call this n equals 1 energy level. So this is the electron here, right? And since this is n equals 1, we can label this system as being in the state ket of psi 1. Also, the electron can choose to be a little bit farther away. So this is n equals 1 energy level. The electron can be at n equals 2 energy level or farther away. Let's say n equals 2 for now. And we can label this as being the ket of psi 2. And this can go on for up to psi n for the nth energy state. Okay. Another example that I can think of the top of my head is the free electron. So if the electron is completely free, it's not near to the proton and electrostatically attracted to the proton, the free electron can be anywhere or at any location at any given time. So the free electron can be anywhere. So just that word alone then implies that there are infinite number of possible states for the free electron. Why? Because it can be at x equals 0 location. We can write this as psi ket of 0, or it can be at x equals 0.1. This is a different state, and we write it as psi of 0.1, or it can be at x equals 101.1 location, and we can write this as psi 101.1 ket. Okay, and there is infinite number of possible states for the free electron. Right. So hopefully the notion of this abstract object called the ket is clear. Is basically describing the state of our system. Now, how do we make the connection between this abstract object and real world measurements or experiments? So let's say we want to measure a quantity. Let's call that quantity momentum. So we want to measure momentum of our state, momentum of a system. Then what do we do? Well, we know we are labeling the state or of the system as with a psi, right? To measure its momentum, we simply ask the momentum of the state. How do we do that? On that state, we act it with an operator. We call that operator. To measure momentum, we have the momentum operator. we denote it with a hat. Okay, so this thing is the momentum operator. So operators are also mathematical objects. In the context of quantum mechanics, they act on state vectors to give you a certain value for the measurement. Okay, so let's say that for the hydrogen atom that we discussed, let's say the state of the electron is at psi 1, and I'm trying to measure the momentum. So I basically act on the state with the momentum operator, and this should yield that the electron is in state psi 1, and the value that I will get if I were to measure the system at that point is P1. Okay, and this is the momentum value for the system after we measure it, or if we choose to measure it. So momentum value of the system. Okay. All right. So if the electron is in psi 2, then we can do a similar thing. So we have psi 2, and we measure, or we ask it with the momentum operator, and this yields P2 of psi 2. As simple as that. However, it is not quite so simple already, because in quantum mechanics, we know by now that there are uncertainties involved. So there are uncertainties in QM, right? So it's not so straightforward to say that, okay, we definitely know that the electron is in the state psi 1 or the electron is in state psi 2. And if we were to measure the momentum of that state, we would definitely get P1 or P2. It's not quite so straightforward in quantum mechanics. So the measurements will not always yield values of P1 and P2 simply. Okay. And rather we'll find the state to be in kind of superposition of both of the states psi 1 and psi 2. So in general, a state vector is written as follows. So in general, a general state vector, just psi without ones or twos, that represents the total state of the system, is written as some constant a times psi 1 plus some constant b times psi 2. Okay, so what are these a's and b's? Well, a's and b's are, a represents how often we'll find system in the state psi 1. B represents how often we find the system in psi 2. Okay, so generally the state of the system is a combination of the two possible states. And also another oversimplification is the fact that we are assuming the system to have just two possible states. In reality, a system can be many possible states. So just by writing this general state vector as the combination of the two possible states that we have assumed, we have introduced uncertainty, in the sense that if we were to measure the state of the system or the momentum of the system for this general get, we would sometimes get the state of the electron being at psi 1, or sometimes we'll get psi 2. So every time we make a measurement, there is some variance in our results. So we don't know for certain what the outcome of the measurement will lead to. Okay, so let's try and measure the momentum of our general state. So we act with the momentum operator on our general state. Now, what are we supposed to get? Well, let's first write the momentum operator acting on the state vector psi, but we have written psi as a combination of a psi 1 plus b of psi 2. And so p will act on psi 1 and P will all act on psi 2. Remember, A's and B's are just constants, so there is no consequence of P on A and B. So if we were to do that, then P acting on psi 1, remember the momentum operator acting on psi 1 gives you the value P1. The momentum operator acting on psi 2 gives you the value P2. So simply, we end up with A P1 psi 1 plus B P2 psi 2. Okay. So this kind of a result is not very clear from a straightforward measurement perspective. So this doesn't clearly tell me what am I to get from a certain measurement. And this automatically tells you that there is some statistical probabilistic result to our measurements. So this is where statistical interpretation of quantum mechanics comes in. Okay. So now we'll understand this kind of a thing, or this kind of a measurement, or this kind of a state where we measure the momentum operator being in a combination of different states in a later video. But for now, we'll take a detour and just understand the very basic statistical uh, or tools from statistics that we would need to understand the fundamentals of quantum. So here we take a detour and we learn some statistical tools that will be very important for quantum mechanics. So for now, keep this in mind for a later video. Now we'll get into the nitty-gritties of some statistics. The first concept that we'll need is that of the expectation value. Expectation value. So expectation value, as the name suggests, is kind of very loosely what you would expect from a measurement, or what you would expect from a series of measurements. What you'd expect from numerous measurements. Commonly, expectation values are known with a multitude of different words. We know it as a mean or the average value, and so on. But in quantum mechanics, we usually reserve this term, expectation value, for our studies. Okay? So it is basically the average value that we expect when we repeat an experiment multiple times. So let's study an example to make this thing absolutely clear. Let's say you and a friend are playing a game. You and your friend are now playing a game, and that game involves coin toss. So a coin has two sides. It has a head and it has a tail. Okay. And your friend proposes this game where if every time it had you have a tail landing, then you win, and you winning implies that your friend pays you an amount of $1.5 or $1.50. Okay. And every time you measure or the coin lands on a head, this implies that your friend wins. So she wins, and she winning and her winning, sorry, um, leads to the fact that you pay her $1. Okay. This is what the game really is. Okay. And before getting into the game, you would want to make some statistical likelihood, like you want to examine some statistical likelihood of whether you are losing money or whether you're winning money, so that you are not dirt poor at the end of the game. But remember, this is a pretty easy game to play at because the amount is not very much. So firstly, we would need the concept of probability, right? So probability tells me that the probability Now, capital P represents probability of the coin landing on a head is the same as the probability of the coin landing on a tail, because there are two sides of a coin and either it lands on a head or lands on a tail. There's only one head, there's only one tail. So it's 1 by 2. So there are two possible outcomes. You are interested in one, either a head or a tail. So the probability is 1/2 for both. So now let's call this head, the probability of head, as P1, and let's call the probability tail P2. So whenever there's a tail, so there's a 50% chance you win. And whenever there is a head, there is a 50% chance that your friend wins and you lose. Okay. So whenever there is a head, your outcome, the outcome for you is minus $1 because you lose money. And whenever there is a tail, the outcome for you is plus 1.5 or $1.50. Okay, so you'll win $1.50. So now we would like to calculate the expectation value. So if you were to play this game multiple times, what would you expect? The expectation value is usually written like this. So exp value and closed inequality sign. So this is the notation we use for expectation value. How do we calculate it? Well, the formula for calculating expectation values is essentially the sum over xi times pi. Now let's unpack that statement. So there are two possible outcomes for you. Either you win $1.50 or you lose $1. So I is the number of possible outcomes. So there are two. So I is from 1 to 2 in this simple game. X sub I represents your outcome. So X sub I is IF outcome for you, and P sub I is the probability of the IF outcome. IF outcome. All right. And at the end, we sum over all of the possible products of this. So let's calculate it for the simple game. So the first outcome for you is either is that you lose $1. Right? So we have minus 1. And what is the probability that you lose $1? It's just 1/2 or 0.5. To that we add plus you win 150, so $1.50. And what is the probability of that happening? That's also 0.5. So a simple calculation tells you that your expectation value is plus 0.25, so $0.25. Okay, so this means on average you would make a profit. You'd make a profit if you were to play the game. So what would that profit be? Let's say you play the game twice. So let's say you're playing the game two games. Two games, that tells me, let's say that we assume that you win one and you lose one. So when you win one, you gain $1.50, and if you lose one, you lose $1. Sorry. And ultimately, what is the net amount that you win or lose? The net is simply 50 cents. So essentially, you're 50 cents more than when you started the game. So per game, you're winning 25 cents. So every time you're playing the game, you're making a profit of 25 cents. So the expectation value suggests that it's a very safe game for you since you're winning. And so you'd go ahead and play the game. But now remember, there are always uncertainties in statistics and especially in quantum measurements. If we were to think about quantum nature of things. So to comprehend such uncertainties and so also sometimes the expectation values are not enough to tell you whether you should proceed with a probabilistic game like this or not. Uh, to make the correct choice, we need another concept from statistics, and that is the concept of standard deviation. Okay, so the standard deviation is a quantity that tells you by how much uh, your measurements are spread out around uh, the expectation point. So by how much the measurements are spread out around the expectation value. Okay. And how do we calculate that? We use sigma to denote our standard deviation. So this is a Greek letter called sigma, and sigma is defined to be the square root of the expectation value of x squared minus the expectation value of x whole square. Okay, and these two are different. They're generally not the same. So the result of a standard deviation is always going to be greater than or equal to 0. If the standard deviation is 0, that means there is no spread, and maybe the data looks something like this, like a delta function. If it's greater than 0, then that means the data is spread around like that. So this may be your expectation value. Okay, so there is some sort of a spread around your expectation value. Okay, so how we know how to measure or how to calculate expectation value of x. How do we do it for expectation value of x squared? So expectation value of x squared is nothing but the square of x for every ith outcome weighted by the probability of the ith outcome, and then you the sum over the whole product. Okay. Now for our simple game, let's calculate what the standard deviation is. So sigma, for our case, would be first there's a square root, and then we have to calculate we have to calculate expectation of x squared. So your outcomes were -$1, so -1 times the probability 0.5. But remember, you have to do -1 squared because this is the expectation value of x squared, so ith squared. Plus, if you win, you were to win $1.50, and that's also squared, times the probability, which is still 0.5. This is the expectation value of x squared. To that, we add our expectation value that we already calculated, which was 0.25, and then we just simply square it. Sorry, we don't add, we subtract. So the expectation value 0.25 squared, and this comes out to be $1.25. So this tells me that if you were to play the game multiple times, then the results would be spread out by this amount, 1.25. Okay, so the expectation value was, remember, you would win 0.25 per game, or you would on average win 0.25. But if you were to play this game multiple times, the measurements would not be so far away from the expectation value. So it's also telling you that the odds are pretty good for you to win. So this implies odds are safe because you're not going to lose that much money. If you win, you're going to win any amount that's already greater than what you have. So it's going to be pretty safe. However, let's up the ante here. Let's say that, remember, whenever there was a tails, win, you win. And let's say now if you win, your friend pays you $10,000. All right, $10,000. Your friend pays. But if you were to lose, in other words, if it were to land on a heads, then you would pay her. So for you, the outcome would be negative $10,000. Sorry, let's say that this is forgot the 50 cents. And if you lose, you pay 10,000. Okay. And this is what you pay. Then, if you were to make a calculation, a quick calculation would reveal that the expectation value of your X is still 0.25. So the expectation value of X just means the expected outcome of this experiment for you would be still 0.25. So you would think initially, okay, this is the same game. But remember, you're either losing 10,000 or just gaining 10,050 cents. So if you were to now calculate the standard deviation in your outcomes, X, is now not only 1.25 that like it was before, but rather it's $10,000.25. So now this automatically tells you, okay, the expectation value is for you to make a profit of $0.25 or 25 cents. But if you were to play this game even just 2 times, there is a possibility that you could lose over $10,000. So that means the odds of this game are now not in your favor. You're not certainly gaining money. You're not certainly gaining $10,000.50, and you're in risk of losing $10,000. So now the odds have become very dangerous, and you should not be gambling with that amount of money, right? And so these are the two most important concepts that we implement in quantum mechanics. And in the next video, we'll look back at our concept of how we will make sense of these sorts of measurements using the concepts of expectation value and standard deviation and probability that we have reviewed in this video. Hope to see you on the next one. Thanks.